Right. Okay. So that's that. So then it's my pleasure to introduce our speaker today, who is Chen-Yu Wei. Chen-Yu is a fourth-year PhD student at the University of Southern California. He's advised by Haipeng Luo. Before that, he did his master's and BS at the National Taiwan University, where he started to do awesome research on MDPs and stochastic games. And ever since that, he's been producing really fantastic work with Haipeng on bandits, adversarial bandits, MDPs, learning in games, all sorts of exciting things that are relevant for this topic of this seminar. We could have invited him to talk about like any of his recent amazing papers, but what he's going to be doing today is talking about learning in infinite-horizon MDPs under linear function approximation. So with that, please, Chen, you go ahead. The floor is yours.
Good. Thanks for the introduction. We are really honored to be invited to give this talk, and thanks for all the organizers for creating this event. My name is Chen-Yu Wei. I'm a fourth-year PhD student at University of Southern California. Today, I'm going to tell you about our recent paper, Learning Infinite-horizon Average-reward MDPs with Linear Function Approximation. And this is a joint work with Mehdi Jafarnia-Jahromi, another PhD student at USC, and our advisors Haipeng Luo and Rahul Jain. Let me give a brief overview of this work. This work studies online reinforcement learning in infinite-horizon average-reward MDPs with linear function approximation. In this setting, we are only aware of 3 algorithms that give regret bounds. They are polytext that gives a t to the 3/4 regret bound, where t is the number of interactions with the environments. And EE polytext gets a t to the 4/5 regret bounds, and AAPI gets a t to the 2/3 regret bound. And these regret bounds do not match the known lower bound, square root t. So we would like to see whether the bound can be improved. And also we find that these algorithms make strong uniformly mixing and uniformly excited features assumptions, and we would like to see whether these assumptions can be relaxed. So in this work, we have 2 contributions. The first is that we get a square root t regret bound under the same assumption as polytext and AAPI. And the second one is that we have a first attempt to relax the uniform mixing and the uniformly excited feature assumptions. And we have some motivations of this work. We observed that there is a significant progress in online reinforcement learning with function approximation, like LSVI UCB by Jain et al., eLinear by Zain et al., and FLSVI by Wang et al. Actually, all these excellent works have given talks in this virtual seminar before. However, most of them study the finite horizon, or you can call it episodic setting. And we lack comparable results for infinite horizon discounted or average reward settings. But in the real world, this kind of infinite horizon formulation is particularly relevant when the task is continual or non-stopping. For example, if we use reinforcement learning in traffic light control, or data center optimization, or trading, or self-driving, we can observe that in these problems, it's not like in the finite horizon formulation, the learner state is reset after it reached some goal state. The task is just continuous and non-stopping. So they might be better captured by the infinite horizon problem formulation. And so we indeed need some efficient algorithms for this kind of problems. Okay, then I will formalize our problem setting. We consider Markov decision processes, and I guess you all know the setting of this this problem. So the goal is to introduce some notations. at time t, the learner observes the current state st, and then it takes an action at, and then it receives a reward r of st at, which is assumed to be bounded between -1 and 1. And the environment generates the next state st plus 1 from the transition kernel p of p given st at. And unlike in the episodic setting, the state is never reset during the game. Sorry, we assume that the action space is finite, but the number of states could be infinite. Okay. In the average reward setting, we care about the average reward in the long run. So here we define j pi of s to be the average reward of a policy starting from state s, and then using the policy pi. And we take an average over n steps and takes n to the infinity. And here the policy pi is a general history dependent policy. Then j star of s is the maximum possible j pi of s over all history-dependent policies. The goal of the learner is to behave as good as j star of s1, given that the learner starts from s1, without knowing the transition and the reward in advance. However, there are two facts that make this learning problem too difficult for online reinforcement learning. The first one is that the optimal policy could be history-dependent, although this only happens in the case the number of states is infinite, but this is indeed the case that we consider. And the second is that the optimal average reward is dependent on the initial state S. In this case, it's not difficult to construct some bad examples where the learner has to suffer a linear in T regret. So in order to make the problem more learnable, we make the following assumption. And this is actually a very standard assumption made in the literature. That is, we assume that the Bellman optimality equation holds. That is, there exists Q star, V star, and J star, such that Q star of SA is equal to R of SA minus J star plus the expectation of V star S prime. And we call this and also the Q star, and all these quantities are uniformly bounded. We call this V star, Q star optimal bias functions. So this assumption will imply that the optimal average reward J star will be independent of the starting state. And the optimal, there exists a stationary optimal policy pi star.
Sorry, I have a quick question regarding this. So like, does this also imply that every policy has a stationary distribution, or at least the optimal policy has a stationary distribution? Not necessarily, right?
I think if this holds, then one of the, at least, I mean, there could be multiple optimal policy, right? And but at least one of them will be a stationary one.
Yeah. Well, what I'm asking is whether these policies are going to induce a unique stationary distribution.
Oh, you mean unique stationary distribution? You mean if there are multiple optimal policy?
Yeah.
Will they induce the same?
I mean, and have like two stationary distributions or something.
Oh, sorry, maybe I can.
Yeah, so
so just Gerge is like married to this distributions over the state space or state action space. So he's always wondering about whether these distributions exist or not. And here you're saying that, okay, we are making this assumption about these value functions, whatnot, that they are uniformly bounded. And the question is whether this implies that if you take an optimal stationary policies, which would be greedy with respect to the action wave function written here, whether that would have a well-defined stationary distribution.
Oh.
I don't think that that's true.
Yeah. So like here, I guess like the Markov chain can be even periodic, and this can still hold, right?
Yeah.
Right,
Things like that. Yeah.
Yeah.
But maybe you could define, you can define something a little bit more general, so Chazaro averaging, and then you can get some version of occupancy measures, which would be well defined, I think.
Okay, well, I guess I'm not going to ask about other assumptions.
Yeah.
I'm just going to let you do
Fine.
the talking. Yeah.
Okay.
So yeah, thank you for that.
Okay, then. Okay, let me continue. And so like an example of this assumption is in the tabular case, if you're dealing with a weakly communicating MDP, it will satisfy this assumption. And because there is a stationary optimal policy. So later in this talk, because we only care about stationary policies. So later in the talk, the policy we mentioned will just be this kind of stationary policy. Under this assumption, we consider the case the learner interacts with the environment for capital T steps, and then we evaluate the performance by the regret. The regret is defined as the difference between Tj stars and the cumulative reward of the learner. So Tj star is like the expected total reward the best policy can gain in T steps. So if this is sublinear in T, that it means that the learner behaves as good as the best policy in the long run. And in the tabular case, the minimax regret bound has been established to be square root span of V star times number of states times number of actions times T, where span of V star is like the maximum difference of the bias function V star on two arbitrary states. And in this work, we'd like to see whether the similar bound can hold in the linear function approximation case. So now we briefly review the linear function approximation scheme. Function approximation is used when the number of states or actions are very large, and the learning them could be inefficient if you do it independently. And linear function approximation is just the simplest form of function approximation. There are several different ways of doing linear function approximation. Basically, they assume that there exists some feature mapping phi of SA that lies in RD space that can represent some quantities of the MDP. One assumption that is considered to be the weakest is like the linear Q star assumption, which just assumes that the optimal Q star function is linear in the features. And this is also called the realizability assumption. Second one is the Q pi for all pi assumption that assumes that the Q function of all policy pi could be represented as a linear function of the feature. We will more formally define this Q pi later in the slide. And the last example is a linear MDP assumption, which assumes that the transition kernel and the reward function can be represented as linear function of the features. And it would be straightforward to see that the linear MDP assumption is the strongest, and linear Q pi assumption is second strongest, and linear Q star assumption is the weakest. And later in the talk, we will review which previous work makes which assumption and which assumptions are made by our algorithm. And before that, we will introduce more assumptions that have been made in previous works. The first is called the uniformly mixing assumption that is made in all three previous works. This assumption says that for any state distribution nu, after executing the policy pi for one step, it becomes slightly closer to the stationary distribution under policy pi. And the rate of convergence to the stationary distribution is governed by this T-mix, or mixing time. And the second assumption that has been made by Polytext and AAPI is that under any policy pi, the minimum eigenvalue of this covariance matrix of the feature is bigger than sigma. This guarantees that under any policy, the learner is able to explore the feature space in all directions. And there is another related work, EE Polytext. It does not assume that equation 1 holds for all policy, but just for some policy pi e that is known by the learner. So now we can compare the assumptions and the regret bounds of previous works and our work. First, Polytext and AAPI makes the uniformly mixing and the uniformly excited feature assumptions, and the linear Q pi for all pi assumption. The regret bound they get are t to the 3/4 and t to the 2/3 respectively. I'm omitting the dependence on all other dependencies. And the EE Polytext relax the uniformly excited feature assumption by the pi e assumption that we just mentioned. And it is also based on the linear Q pi assumption. And it gets the t to the 4/5 regret bound. Our first algorithm, MDP-EXP2, is based on the same assumption sets as Polytext and AAPI, but improves the bound to square root t. And while these 4 assumptions on the slide all make the strong explorability assumptions given by UM or UEF or pi e, we have 2 other algorithms that significantly relax them. But on the other hand, we make the stronger linear MDP assumption about the structure of the MDP. The BOE here means the Bellman optimality equation that we mentioned earlier. So this algorithm FOPO gets square root t regret bound, but this is not a computationally efficient algorithm. So we have a remedy for it. This optimistic LSVI algorithm get a t to the 3/4 regret bound, but it's a computationally efficient one. And the relation between assumptions are, as mentioned before, UM plus UEF is stronger than UM plus pi e and stronger than BOE assumptions. And linear MDP is stronger than linear Q pi assumption. And as mentioned before, our contribution has 2. First, the MDP-EXP2 improves the regret bound of Polytext and AAPI under the same assumption. And we have first attempt to relax the strong explorability assumptions. And we will introduce them in part 2 and part 1 respectively. Okay, so do we have questions at this point?
No, it's all very clear.
Okay. Okay,
Or
then.
Chaba wants to ask something. No. He's saying no.
Okay, then we go to part 1. It's about linear MDP without those strong explorability assumption. This is just an overview of the assumption again. First assumption is about linear MDP. So this phi of Si is given to the learner, but not the psi of S prime or the theta. And the second one is the Bellman optimality equation. And the third one is without loss of generality, we assume that the first feature is a constant feature for all state and action. And this assumption will imply that the Q star function will be an inner product of a phi of SA and the unknown W star. Okay, then our algorithm FOPO, which stands for fixed point optimization with optimism, is based on the optimism under the face of uncertainty principle. And this is the algorithm pseudocode. we define the capital lambda T to be the empirical covariance matrix of the features. Then every time when when the determinant of lambda T is doubled, we solve an optimization problem. This optimization problem tries to maximize J under some constraints. This J will be an optimistic estimator for the true optimal average reward J star. So the first constraint might look familiar to you if you know the similar algorithm like LSVI UCB or E-linear that works for the episodic setting. But this WT is just like the solution of a least square problem where you want to fit Wx to Y, where the X is the features and the Y is the things in this bracket. And this is motivated by the Bellman's equation. And this WT is is an estimator of the W star in the Bellman equation. And also we have a vector B that is added to this equation, and it is constrained in an ellipsoid. And this B captures the idea of confidence region that account for the randomness in the transition. And we also have a constraint on the norm of WT because we can show that W star will satisfy this condition.
I have a quick question, if I may. Do we need to know the span of the optimal value function or an upper bound on the span of the optimal value function for the correctness of this algorithm?
Yeah, the learner needs to know span of V star. That's an assumption. Yeah.
Okay.
Yeah, it needs to know.
Maybe we can talk about that later.
Okay. Yeah. So, okay. Then yeah. So after solving this optimization problem, based on the principle of optimism under uncertainty, we will use this WT to make decision. That is, AT is chosen greedily with respect to this WT. Okay. And we can also see that this FOPO is based on the global optimism idea that is developed in Zenet et al. And Gergely and Kera's paper. For this algorithm, it achieves the bound of span of V star times square root D cube to times T. However, the obvious issue of FOPO is that it's not computationally tractable, and as Chaba mentioned, it needs to know some knowledge of span of V star. A remark here is that achieving this kind of span V star times square root T bound with a computationally efficient algorithm is already very non-trivial in the tabular case. A first attempt was done by the Rigel, and this is like ours, is not computationally efficient. And recently it was resolved by Fruit et al. By the algorithm called Scale, and then following work Scale Plus. So it would be interesting to see whether any techniques of them could be useful here to get a computationally efficient algorithm. But it can be foreseen that there will be more challenges in linear MDP case compared to the tabular case. Okay. Still, we would like to make the algorithm efficient, although maybe with a worse constant. Okay, so our attempt one is based on the following ideas. First, we want.
Can we just very quickly ask a question? It's actually this question. The question is whether in the tabular case, these algorithms assume the knowledge of the span of V star or not.
Oh, yes. Also, yeah, in the Scale and Scale Plus, they also need to know the span, yeah, as an input to the algorithm.
I think that there was some attempt to remove this.
Oh, I think In Rigel, or
in Rigel, they definitely say that you don't need to know it. But I'm not sure whether the argument is really spread out. And yeah, maybe we can take this offline. Yeah.
Okay, yeah.
I'm not sure in these papers they do assume, but we can discuss whether this is really needed. Yeah.
Okay, yeah. Okay, so, okay, our attempt one, yeah, based on the following ideas. First, we want to avoid solving a fixed point problem because that seems to be difficult. And second, we try to use local exploration bonus instead of global optimism. This concept was introduced in Gerge and Kera's paper, but it is slightly not unclear how to add exploration bonus to the bias function in the average reward setting. So our third idea is, according to our previous work, for a tabular case, you can just use a discounted algorithm to solve an average reward problem, although the dependence on t could become worse. So now we write out our attempt as follows. This is like the very natural extension of the LSVI UCB algorithm, but translate to the discounted setting. And we can see that the WT now only depends on the previous value function, VT minus 1, which in turn depends only on WT minus 1. And like in LSVI UCB, we add a bonus term to the value function. However, unfortunately, we are unable to show any sublinear regret for this algorithm. And it turns out to analyze this algorithm has slightly more difficulty compared to the tabular case. So our second attempt is even more straightforward. Instead of reducing the problem to a discounted version, we reduce our problem to the episodic version. And in the episodic setting, we can directly use the LSVI UCB algorithm. So we divide the whole horizon into episodes of length h, and then run their algorithm on these episodes. And then it turns out this can work and get us a regret bound of t to the 3/4. And you may wonder why reducing the problem to the discounted one and the episodic one makes some difference. And this is a bit technical, but I can describe the key differences between these two reductions. In the discounted version, you can see that WT depends on WT minus 1, where WT minus 1 is the policy that the learner used in previous step. But in the finite horizon version, WH depends on WH plus 1, and WH plus 1 is the policy that the learner will use in the next step. So this subtle difference makes the analysis different, and we did not successfully analyze the former one. But still, a reduction to the discounted version is actually more desirable. Let's say if you want the algorithm to output a final policy after the training, then the discounted version will give you a stationary policy. But the episodic reduction will give you a fixed length non-stationary policy. And having a non-stationary policy is not very natural in the average reward setting. So this algorithm still leaves much to be desired. Okay, so this end part one, and we have so the summary is that we have a computationally intractable algorithm that gets a square root t regret with span of v star dependence, and a computationally efficient algorithm with t to the 3/4 regret by simply reducing the problem to the episodic setting. And two natural open problems are follows. So we want to have a computationally tractable algorithm for linear MDP that gets square root t regret. And also, Based on our failure in analyzing the attempt 1 algorithm, we hope to analyze sample complexity bound for online reinforcement learning in linear MDP and in infinite horizon discounted setting. So we're not very sure whether this was solved, but to our knowledge, we don't know any sample complexity bound for this setting. So if you know somehow know that there are some related work, maybe you can tell us. So do we have question at this point?
Yeah, so I just wonder why the linear MDP assumption was important for this part. You didn't really emphasize that, like why that was important for this analysis.
Oh, I think in well, I think okay, in this thing, I think the reason is similar to like in the linear or LSVI UCB, we need
so
linear.
Those do not actually need linear MDPs. At least like Eleanor does not require linear MDPs. That only requires zero inherent Bellman error, right? Which is like essentially like all the Q functions are representable by the features.
I see. So you mean we can handle a general function class just with a small inherent Bellman error?
Right.
I see. Yeah. So we did not really look at that direction, but it's possible that this can be extended to that setting. Yeah. I think we make this for simplicity.
Right. I see. Okay. Good. Maybe we can talk about this later once you finish the talk.
Okay. So we
Perfect.
continue.
Thank you. Yeah. Please go ahead.
And okay, then we go to the second part. This is about another algorithm called MDP EXP2. For this part, we need a new set of assumptions. So you can forget about all the assumptions made in the previous part and just consider the assumptions that I list in this slide. First, we assume uniformly mixing. For any policy pi, there exists a stationary policy mu pi, such that for any stationary distribution nu, if the learner executes pi for one step, then the state distribution will become closer to the stationary distribution, and the rate is governed by this T mix or the mixing time. So if this T mix is smaller, that means the convergence to the stationary distribution will be faster. Second, we assume that we have a uniformly excited features. That is, for any pi, the eigenvalue of the covariance matrix under the stationary distribution is larger than sigma. It means that the learner can explore the feature space in all directions of the feature space. Clearly, this simplifies the exploration issue a lot. We can show that under the mixing assumption, the average reward of a policy is independent of the initial state, and that the following Bellman equation for policy pi will hold. Then we assume the Q pi is linear in the features, and this is weaker than linear MDP assumption mentioned before. And as before, we make without loss of generality assumption that the first feature is always 1. Okay. And before I describe our algorithm, I want to first describe where our algorithm is inspired from. It's inspired from the adversarial linear bandit algorithm called EXP2. Below, I briefly describe the adversarial linear bandit problem and this algorithm. And one can think of the linear bandit problem as a single-state MDP problem, where the reward is linear function of the features. We assume there is a fixed action set A, and a feature mapping that, and there is a feature mapping that maps every action to a d-dimensional vector, given by written as phi of A. The action distribution pi1 is initialized as uniform, and at each time t, the algorithm draws an action AT from the action distribution pi t. And then upon receive the reward, it will observe the reward as an inner product of the feature at AT and an unknown WT, which we refer to as a reward vector. And WT can be adversarially chosen. And the learner will construct a WT hat, which is an unbiased estimator for WT. Then the learner will do an exponential weight update using this WT hat. So this is a very simple algorithm. And the regret is defined as the difference between the cumulative reward of the best action distribution and the cumulative reward of the learner. And then now we would like to reduce the MDP problem to a linear bandit problem. This is through the very powerful lemma called performance difference lemma, which is used in the analysis of almost every policy optimization method. So one can decompose the regret of the MDP problem to the regret of an online learning problem on every state, where a q pi k of SA is like the reward of action A on state S. Then by the linear q pi assumption, we can replace q pi k of SA to phi of SA inner product W pi k. So this part is just like the regret of a linear bandit problem, where phi of SA is like the feature of the actions in the linear bandit, and W of pi k is like the unknown reward vector in linear bandits. And since this pi k is changing over k, by the way, k is the index of the update of the policy. And this pi k is changing over k, so we would like to use a linear bandit algorithm that can handle changing reward or adversarial reward. However, different from linear bandit, the learner does not observe this inner product. But observe that one can add any constant c beside the reward and does not affect the regret bound, because it can be canceled after you sum over actions, and it will be sufficient to construct the WK hat that makes the expectation of phi of SA transpose WK hat equal to the red part. And then if you have this, then you can plug in this WK hat to the exponential weight algorithm that we mentioned in the previous slide. So now the problem boils down to the following problem. Given some policy pi, how to construct a W hat such that this expectation hold. And our solution is as follows. We execute pi for 2m_n steps, where m is of order 1 over sigma. The sigma is the minimum eigenvalue of the covariance matrix that we mentioned before. And n is of order mixing time. Then in these 2m_n steps, we collect m trajectory, each of length n. So we only use half of the samples that we obtained. And how exactly is this done? This is illustrated in this figure. This line is the timeline, and it is divided into intervals of length n. We discard the samples in the first interval, and then collect samples in the second interval, and then again discard samples in the third interval, and then collect sample in the 4th interval, and so on. And we denote the state and action that we encountered in the first step of every interval as S superscript I and A superscript I, and the total reward in the ith interval that we collect is denoted as R superscript I. And why do we do it in this way? Because we want to ensure that the state distribution at the first step of each interval that we collect are almost independently sampled from the stationary distribution. This will be helpful for us to get an unbiased estimator. And because starting from any state, after the learner walks for T mix steps, the state distribution will roughly be reset to mu pi, the stationary distribution. So after the algorithm collect a trajectory of length n, it will take a rest for another n steps, and then we can ensure that the samples in the next trajectory will be almost independent from the previous trajectories. And then the way we construct the reward estimator is inspired from the EXP2 algorithm. You will calculate the covariance matrix lambda, and then the reward estimator W hat is the inverse of lambda times the weighted feature vector. The weight is given by the reward. And basically, we can prove that with this W hat, the property we want will hold approximately. And it only holds approximately because there's still some correlation between the trajectories, but it can be very small if n is sufficiently larger than T mix. So now the whole MDP-XP2 algorithm is as follows. Let K be the policy update index. And for each K, we execute pi K for roughly T mix over sigma steps and construct WK hat as described in the previous slide. And we update the policy using the exponential weight algorithm. And for this simple algorithm, we can get a regret bound that is square root in T and having some other dependencies on sigma and mixing time. Okay. In this page, we compare our algorithm, the analysis in our algorithm and previous works. So we observe that polytext and AAP are also based on exponential weight update algorithm, but the regret bound is slightly suboptimal. So the key is in the both in the analysis and also the way we construct the WK hat. So in the previous work, they used a least square policy evaluation algorithm to construct WK hat and argue that this is an epsilon accurate estimator of the true W pi K. If the learner use 1 over epsilon square samples to construct the WK hat. But in our analysis, we use a way that is more like EXP2 to construct WK hat and argue that it is an unbiased version of the WK unbiased estimator of a translated version of W pi K. It has constant variance and with just the O1 samples. Here, O hides some constant that is related to T mix and sigma. So in this view, polytext and API are more like approximating a first order optimization method, but MDP-XP2 is more like a 0th order optimization method. And it turns out overall, the second kind of arguments could give a better sample complexity bound. And then in this slide, I just draw a connection with between the MDP-XP2 algorithm with natural policy gradient. It is already a folklore that the exponential weight algorithm is connected to the natural policy gradient algorithm over simplex policy, softmax policies, and is also connected with the TRPO and PPO. But in these works, the connection is derived from some with a lot of mathematical derivation. But here we show that if you view the exponential weight algorithm from the view of linear bandit, their update form is very similar in themselves. So recall that our algorithm is a soft in the MDP-XP2 algorithm. The policy update is like this. Every time you update the theta k with this covariance matrix inverse times the reward weighted feature vectors. And if you write an update of a natural policy gradient, it is like this. Each time the theta is updated with the inverse of Fisher information matrix times the reinforced gradient estimator. And if you calculate the Fisher information matrix of this softmax policy, you'll find that this is almost same as the covariance matrix used in linear bandit. And the second reinforced estimator is like the second thing in our, it's like this weighted feature vector. Okay, so this correspondence is very clear and simple. And now we end part 2 with some open problems. So the first is that is the same regret bound achievable if the learner does not know T mix and sigma. We can actually get some suboptimal bound if we without knowing T mix and sigma. But can we get the same bound if we don't know them? And how to relax those explorability assumptions. So some attempt was already made by EE Polytext, but maybe there are some other ways, for example, adding bonus to the exponential weight algorithm. And here I copy the open problem that I listed in the end of part 1. Yeah, so we want a scarcity regret bound for general linear MDP, and we want a sample complexity bound for online reinforcement learning in linear MDP and in the infinite horizon discounted setting. And in this last slide, I again summarize the results. We have 2 main results. The first is that we improved the regret bound of Polytext and AAPI under the same setting. And the second is that we have some attempt to relax the UM and UEF assumptions in this linear function approximation setting. So that's it. And thank you for the listening. I'm taking questions. Thanks.
All right. Thank you very much. Let's give a little applause to Chen-Yu. Yeah, there we go. All right, yeah, thank you. That was fantastic, and I'm really impressed by these results. I guess I first have like a similar question as I had for the first part. So like, what assumptions did you use in this case, and why were they necessary? So I understand that for this part of the talk, you needed uniform mixing. Well, I guess I understand like the uniform excitement part, but why did you need the uniform mixing?
Oh, it's like the uniform. It is required because the length of this red interval, it should be at least like a T mix, so that because a T mix, when you want to approximate the Q value starting from this state action pair, the learner needs to collect long enough trajectory to approximate it. So that's where the mixing time comes from.
Right, but for this actually, it suffices to make like a milder assumption about mixing as well, right? Because here you say that you require like one-step mixing, one-step exponential mixing for any distribution and any policy.
Yes.
And this is actually like a much milder assumption that says that you can actually have like multi-step mixing.
That's indeed that should be possible, because that was made by our previous work, and this just makes the analysis much simpler.
Right. Yeah. But if you think about it, this is a ridiculously strong assumption, right? So it's right. So if you multiply the right hand side by some large constant c, then it's a lot more realistic, and yet what you need in that analysis is still satisfied.
Right. Yeah, this should be able to become slightly weaker.
All right, thank you. So I don't know, like Chaba, do you want to?
Oh, I'm answering actually it's a question or made an attempt, but I think actually maybe he should come and ask his question. There were actually 2 questions in the chat before I would get to my questions. Maybe actually, do you want to ask your question?
Sure.
Go ahead.
Can you hear me?
Yeah.
So Chen-Yu, thanks. I was just wondering, so you mentioned this open problem of like maybe you can use a bonus to get square root t regret and on the second part.
Yeah, right.
I guess I'm a little concerned about it, because if you add a bonus, then maybe that's not a valid QPy function, so it won't be linearly realizable. And if you change the reward function, then you might break your realizability structure, right?
Yeah, that's true. So this is just we did not attempt to do this. This is just some really random.
Okay, so
can you elaborate why that would be a problem? Because I mean, like, sure, like the estimated action value function or action value function plus the bonus is not linear, but why is that the problem?
I guess you have to do a Bellman backup of that thing as well, maybe.
Sure. I mean, you don't really need to do that. You could do policy iteration. Effectively, that's what you're doing, right? Like, you take this exponential, like, Boltzmann thing, and then at least the new policy. Know that you have the policy. It's actually very fun. Great.
I see what you're saying. Yeah. So okay, that might be the case. I guess it depends on how you add the bonus. Like if you regress onto reward plus bonus, then you're in trouble. But if you do regress onto just reward and then add bonus after the fact, you're okay.
Yeah. Well, there is a reason this is an open problem.
Yeah. Okay. That's all. Thanks.
Yeah. It's a fun problem to think about.
Yeah.
Okay, so there was a question from Vector Devanto. Do you want to ask your question, Vector?
Oh yeah, thanks, Java. Can you hear me?
Yeah.
Chen, could you please explain again your argument on the connection between your proposed algorithm and natural policy gradient?
Oh,
I was missing that. Sorry.
Oh, it's okay. The connection. So I list the algorithm update here. So this is like our algorithm, and this is the standard MPG algorithm. And the connection is that first, the form is very similar. And if you identify this phi of SA to this gradient log pi, if you identify this with then they are of the same form, right?
I guess I have a related question to this actually. This is one of my listed questions. So they're not quite the same though, right? Like there is a normalizing factor.
Yeah, right.
And some of the gradient of that would come in NPG, which doesn't come in this MDP XP2. So then, what the heck? Which one is the real algorithm? Or maybe that difference is not significant, or like what's your hunch on this?
Well, I think, yeah, so I think in this Argolos et al.'s paper, they actually have another version of MPG called QMPG. That's that becomes yeah, that exactly remove that normalizing factor, and
But
it becomes the same. Sorry,
that's not MPG.
yeah, that's not MPG. Yeah, right, that's true.
So
But
you're betting on that maybe we should not focus on MPG that much. It's good that we have this MDP XP2 that this is good enough. We understand it. And is that what you're saying?
Well, don't make him say it on the record, Chaba.
Yeah.
This is controversial.
And then everything is controversial.
Yep.
But
Right. Thanks, Chen-Yu.
Does this make sense? Yeah.
Yes. All right.
Okay.
Thanks.
All right. So in the meanwhile, there are questions about mixing. All right. So Pan, do you wanna ask your question, Penshu?
Yes. Hi.
Hi.
This is Pan from UCLA. Yeah, I'm just not quite sure why you need to know the exact mixing times in the regret bounds. It seems to me that you can just replace it by some log 1 over epsilon, since you have the mixing assumption, right?
So some increasing sequence, and then like eventually it becomes larger than mixing time, and by the time it starts to work, and like.
Oh, yeah. Is that what you mean? You mean increasing schedule length?
Yeah, I mean in the open problem 1, you see that you need to know the T mix to set the absolute length of the learning, but can we just set it to be just log 1 over epsilon, so that the mixing assumption holds with some epsilon error or something? In that way, you don't need to keep it in the regret bound, right?
Yeah, I see what you mean, but that's what I'm saying. Because that potentially worse the regret bound, make the regret bound worse if you do an increasing scheduling.
Yeah, then we are in this really interesting territory where asymptotically you can almost match the original regret bound, but not quite. And finite time, like the difference could be really huge, right? So if you care about, worst case finite time bounds with controlled constants, then this is not really great.
Will that just affect the regret bound by just some log factors, or it will increase the order or something?
I did not do the calculation, so I'm not sure. But yeah, it depends on how you do the schedule, increasing the schedule. It can be how much it will work the regret bound.
I think, Ben, what happens is that if you have a finite, like you care about the finite time bound, and you introduce this increasing sequence, then depending on how big the mixing time is, either you are in a vacuous regime, or you start to get meaningful bonds, and the range of the MDPs for which the mixing time is sufficiently small so that your fixed schedule works is going to be limited, and like that kind of like captures what is happening there. And then the question is whether you're happy that your schedule is limiting what MDPs you can deal with. Essentially, that's what's happening for a finite time case, no matter what you do. in the limit, like you can say that, oh, asymptotically, you're only losing whatever, log, anything. You can do that.
Yeah.
But effectively, you're losing a bunch of MDPs. And then the question is, all right, is that really necessary?
I see. Yes, thanks
course,
for
there
this.
is a mixing time which is so big that it's much bigger than your horizon. Then like you don't care about the MDPs, but like at least for the MDPs for which the mixing time is not that big, and then maybe there is a way to do this.
I see. Thank you.
Thank you.
Oh, I had a question related to the mixing time. So in the analysis you're doing, or no, so in the algorithm you're doing the blocking technique, right? And one imagines that you could just like not do it and just do this in the analysis. But now, of course, I understand the biasness, unbiasedness thing comes out, but you still have some bias, which is because the samples are actually correlated. So I wonder whether this is really a necessary part of the algorithm, this blocking way of estimating things, or it just makes the analysis cleaner and simpler. And you think that the analysis would go through. If you had the blocks, you would do the estimation over the blocks. So you need the blocks, but like you can use all the samples. Like you don't need to, leave with half of the samples.
I see. But okay, but I think in this, yeah, we can collect all the samples, but maybe in this, when we construct this W hat,
yeah,
we need to use this disjoint intervals in summing.
Is this really necessary? That's what I'm asking, because it's like, like when you have this mixing time series and then people do the analysis, then they usually don't throw away samples, but in the analysis, they introduce the blocking technique and they show that there is, things decoupled, so to say.
Okay.
Concentrations happening.
I see. I guess I'm not so sure. So yeah, I don't know how to do. I think I didn't see the analysis that you mentioned. Okay. Yeah, before. So yeah, I don't know how to do blocking only in the analysis.
Offline.
Okay.
There's a bunch of papers that were doing this.
Okay.
Right. So actually, I had some questions also regarding this blocking thing. I just find it really surprising that you managed to make this work, because it seems that you're throwing away a lot of data, right?
It's just half.
No, not just half. It's like within like any time window, you're really only using the data from this period, right? None of the past data, right? You're not using any of the past observed features.
Right.
But I understand that you argue that this allows you to construct like a constant variance estimate that is like reasonably unbiased, and that is enough for this adversarial kind of like least squares estimators that you're relying on.
I guess the reduction of the data comes from the mixing time, right? Like, because you have the block length, that's n, and that's proportional to the mixing time. So you're effectively, so like for every block, you need a summary, and then like you take the estimates over the blocks. So then the number of blocks is the number of interactions divided by mixing time. That has the reduction, but that's sort of necessary if you have mixing time series. I'm like, even if you didn't do any of the blocking, you just constructed a moving window least squares estimate, the analysis would show that like you kind of like, this is your effective sample size. It is like divided by the mixing time. That's my previous experience. It has similar situations. So I wouldn't worry that much about that. Although it's, yeah, like it's more like the bigger question is that, okay, like we're bringing all this mixing, whatnot. It's really convenient for the analysis, But then the other line of work that you were also doing, that as the bonus whatnot avoids all of this. That's really intriguing. That, like, because here the mixing time for some of the policies could be really bad that you encounter. But then maybe there is some argument that says that if you would be optimistic, then you only improve your mixing or whatnot.
Yeah, that's interesting.